leave a ring further out for bullets that don't go as far, and so you get a uranium radiohalo where you know that there was uranium in the centre, produces 8 rings. The distances from the zircon are equivalent to the energies of the alpha particles, and you can actually work out which step in the decay from uranium down to lead produced each of those rings. So you've got the first decay step is when uranium-238 decays down to uranium-234. That has that top energy, and you can see it's one of the weaker decays, and it forms a ring closer into the zircon. But the step from polonium-218 down to polonium-214 is 50% more energetic, and so it has a ring further out. So this is significant. You can actually not only see the physical evidence that there has been radioactive decay, because you see some creationists used to argue maybe there wasn't any radioactive decay, that the chemical analyses have just been interpreted by the geologists as radioactive dates. Maybe there wasn't any radioactive decay. Well, the radiohalos are physical evidence that radioactive decay has occurred in the rocks. So the alpha particles ejected at each of the different decay steps of uranium have different energy, so these bullets travel different distances into the surrounding biotite, ideally producing 8 different rings in what then becomes known as a uranium radiohalo, because the parent of these alpha particles was uranium in that zircon crystal. Okay, I hope you're following me there. And there's a photograph of one of these fully formed dark uranium radiohalos with 8 rings. Now the biotite looks black in a hand specimen, but under the microscope it can look green or brown or orange, as you can see here, because it's so thin, light can pass through it. Now it has been determined that to fully form a dark uranium radiohalo requires 500 million to 1 billion alpha particles to get the intensity of the damage to the biotite crystal so that it's visible under the microscope. You need at least 500 million to 1 billion alpha decays. And that is equivalent to 100 million years worth of radioactive decay at today's measured rates. So when you see that radiohalo under the microscope in a granite, it means that there has been so much radioactive decay, it's the equivalent of at least 100 million years worth at today's measured rates. Now that's not to say there was 100 million years worth of decay, it's just that number of alpha particles equivalent to that amount of decay. And that's important to remember the difference. That's why you'll always see in brackets at today's decay rate. That's assuming today's slow rate of decay. Now, granites around the world contain these dark uranium radiohalos. There's a number of granites that I've looked at in the Grand Canyon, in southern Australia, in southeastern Australia, in the Lake District of England. In fact, I'm going to talk about that granite in a paper at the conference in Pittsburgh next month. And in Stone Mountain in Georgia, where the Confederate Memorial is, we see granite that contains uranium radiohalos. And the Half Dome granite in Yosemite National Park, the biotite in it contains uranium radiohalos. So granites contain observable physical evidence of abundant nuclear decay, at least 100 million years worth at today's decay rates. However, in the same granites, in the same biotite flakes, with the uranium radiohalos, we find other types of radiohalos. Now, the big one there is, it looks so blurred, take my word for it, it's a uranium radiohalo, the big one you see there. on the left. Okay? The reason why it's so blurred is because there's been more than 100 million years worth of decay involved. There's been so many alpha particles, the rings have become blurred. It's just become a mass of alteration, damage to the crystal. But next to it, you can see a much smaller radiohalo that only has one small ring, an outer ring, and everything inside of it is dark from the alteration. It consists of only one ring and it's smaller. Then we go to other biotite flakes where we see radiohalos that consist of two rings. And take my word for it, there is a lighter outer ring of that other radiohalo in the crack. So you get one ring radiohalos, two ring radiohalos, whereas the uranium has 8 rings. We also find radiohalos that consist of only 3 rings. And there are 3 rings there. It doesn't show up well on the screen. But in the blurred area of that central dark area, there are actually 2 rings close together, and there is an outer ring. Now, because we can measure the radii, or the diameter of those rings, we can actually work out what elements were responsible. The top right-hand corner, we see a cut-down version of the earlier diagram with the 8 rings of a uranium radiohalo. Okay, and again the same list of parent and the energies. Look at the rings where we have the 1 ring, the 2 ring and the 3 rings. They correspond to the last 3 isotopes in the decay chain, the 3 polonium isotopes, polonium-218, 214 and 210. Now, the 1 ring halo only has the ring for polonium-210, so we call that a polonium-210 halo. The red one, the bottom left here, it has 2 rings, the ring for polonium-210 and the ring for polonium-214, so we call that a polonium-214 halo. And the one with the 3